3, Chapter 1, Introduction to Scaling Networks. So we're going to go over just real quick, because I know you guys have all already read this or are going to read it again, but we're going to go over this chapter. And so it's properly titled with the Introduction to Scaling Networks. Okay, and so apparently we're going to describe the use of hierarchical networks for a small business. Describe recommendations for designing a network that is scalable. Select the appropriate switch and hardware. Describe the types of routers available for small to medium-sized businesses and configure basic settings on a Cisco device. Alright, so basically it's telling you right here from the beginning that all of CCNA3 is going to be taking what we've learned so far and implementing it for medium to large-sized businesses. Basically, we have worked on smaller businesses designs in the past, and we are going to move on past that into the great scaling of networks. Alright, so the CCNA3 turns out to be probably the hardest CCNA because it's taking the concepts that you've used, and I know nobody has forgotten any of them, and what we're going to do with them is make them more complex. You know, that's what you guys needed, is just we need a little more complex design. And really, I think it is one of the more fun CCNAs. You're doing a lot of cool stuff, but yeah, it's easy to get behind. You might have to go back to CCNA2 and look at some of these things. Alright, so I'm going to try to catch you up as we go along. Alright, what do we have going on here? Oh, we don't need to do this class activity. Okay, the need to scale the network. Alright, well, let's watch a little video here. A small single location for a company. Alright, and so now what's going to happen? Oh, the internet comes in. We have more employees, so now we have 2 sites, and so we're scaling our networks for increased business size and to go to different places. Super neat. Okay. Next, enterprise business devices. Okay, is there anything really important here? I don't know. Alright, so what is this actually showing? So we have our large enterprise network, as it says right here. Okay, so this right here is what we're going to call a core switch or a distribution switch. It's the core right, actually it's distribution right there. It'd be the core right here. So what it's feeding into what we consider the WAN module. Okay, so what is the WAN module doing? It's connecting remote sites. Alright, so it's one way. And so WAN is where we're talking about private connections, stuff like MPLS, ATM, where we're probably renting an expensive optical line or T1, T3, something that is going to, well, we know with our definition of WAN, it's going a large distance, and so it's going across town or it's going across the country to these different sites. Alright, so PSTN. What is this? Plain Switch Telephone Network? I don't remember what the actual acronym for that is, but that is your telephone network. And so that's your phone blocks. Maybe you're not doing VoIP, and so you're going over that, or hopefully you're not doing you know, the old 56K. And then we have the internet. Okay, and so the internet is the opposite of WAN. These WAN connections, they're private, and so they're just going from one site to another, connecting the same business, where the internet, as we all know, is connecting many networks. Alright, let's see, what do they have here? Well, as you can see, each one of these little sites has a data center. I'm not really sure why they did that, and well, we'll just go on to the design here. Alright, so here is our base design. Alright, so we have our 3 layers, the core, right? And the core, basically, it's pure and simple. Dirty roll is just high-speed switching. This connection right here is usually 10 gig, if not 40 gig. And usually when we see this in the core, this is what we call a virtual switching stack BSS, and it actually, these two devices are virtually stacked in different locations, and so they are completely redundant. They work almost as one device, and where that is nice is if we have to update anything, and just redundancy. Okay. As you can see, the core is connecting to these router looking things with brick wall. That's going to be our firewall. Maybe it's a router working as a firewall, something like that, and it's going to keep us safe from the internet. Okay, then we have our distribution. Our distribution is the real workhorse. It is where typically this side right here is the layer 3, and the side down to the axis is all layer 2 connectivity, right? So we have IP switching up here, and then just straight MAC address layer 2 switching down here. So in the more modern networks, actually layer 3 goes all the way down, but in the past that's what the distribution does. And so the distribution is probably where we're going to have our bigger access lists. It's going to start off the routing protocols and feed to the core layer, and it is where all the wire closets come to these distribution switches to feed to them, and then we have our access. And so what's happening at our access? Well, we're connecting all of our end devices. We're doing a little QoS. We have power over Ethernet on our access switches, so we can power these phones with just an Ethernet cable so that they can then give internet to this computer and all kinds of cool stuff. Let's see if they tell us anything good here yet. No, they do not. Alright, so that's just my base on the 3-layer design. Core, high-speed switching, distribution layer, the workhorse of everything. Our access layer is then where end devices connect, and we are going to have a little QoS, and we could have, I don't know, layer 2 MAC address filtering, something like that. Okay. Now we're going to go to figure 2, which is what LCSC runs on in most companies around Lewiston, but not all companies. And well, actually this isn't what I was looking for. Where's our figure 2? Alright, here we go. We're back to it. And so this is a collapse core, and in the collapse core you see that we no longer have this 3-tier. And so a collapse core is designed for a smaller network, or maybe we just don't have the money. Alright, because each one of these, if we go back to this picture, we're talking about very, very expensive switches. So these are probably a 6500 series. These could be 6500 series or 4500 series, or there's a lot of different choices now. But anyways, we'll go over that later on this chapter. But anyhow, these switches are 6500s. If we get them big enough, they could be well over $100,000. And so, and just so you guys know, there's more than 2 switches in this entire network. There's probably multiple distribution switches. There might only be 2 core switches, and then there's a lot more than 5 switches down here. This is a bigger network. It's just we're going to scale it. But all right, back to the collapse core. So the collapse core, instead of having all that redundancy, we actually merge our distribution layer with our core layer. And so we have the distribution and the core layer all in one layer, so there's not just switches dedicated to high-speed switching. We still have our access layer, and so the core and the distribution, all of it's happening right here in the collapse core, and then we have our access layer doing the same stuff it was doing before. Alright, so let's keep moving. Alright, so enterprise architecture. This is Cisco. In fact, you can get an entire certification on this Cisco architecture. It's called a Cisco Certified Design Associate, or you can become a design professional if you want to go on. And basically, this CCDA is based on what we see right here. It goes much more advanced into it, right? And so we have our enterprise campus, and so as you guys will notice our enterprise campus is that layer that we were just looking at. We have the access layer, the distribution, and the core. Alright, and so now it's given us our server farm data center module. Okay, so that's coming off of the core, as you can see, right? Because why would we have high-speed switching? Because it's going to our resources in the data center. Alright, so then coming off of the core in this direction, so now we're taking this picture sideways. So if we go back to our firewalls right here, you notice that they look similar to what we're seeing in these enterprise edge modules. Okay, so perhaps we have our e-commerce. Alright, and so what is e-commerce? I hope you guys know. Let's see, what does it say? Oh, it doesn't even have e-commerce on it. Anyhow, so e-commerce, what it's doing is that's our online sales, and so for some reason it's going to ISP A and ISP B because we're in a big company, and so we want redundant connections so people can definitely always get to our website to buy our merchandise. Alright. Then we have our internet connectivity. And if you notice, internet connectivity is going to ISP1, ISP2, and the phone system. Alright, so we could actually do copper if we wanted to. I guess we have a backup 56K connection to the internet. Great. So what we're looking at there is the internet connectivity is a firewall that is connecting us to our enterprise branch. I don't know what else is doing. Our telework. Now, that'd be through our VPN. Alright, so anyways, our internet connectivity, it's basically just a firewall giving us access to, well, I think you guys can figure out what the internet gives us access to. Alright, so that's one part of the edge. So then we go to the remote access and VPN. And so if you guys have forgotten what a VPN is where we form a virtual private network across. Okay, so we have our core over here, and our enterprise branch is over here. And so what is our enterprise branch doing? If we want to access their network over the internet, alright, see how this is tied into the internet? We don't want our communications for everyone to see. That's how we get in trouble, right? And especially if we're, I don't know, like Schweitzer Engineering making secret products or whatnot. We don't want our products being stolen. And so we use a VPN to go into the internet and encrypt a connection so that these two they think that they are in the same private network, right? Because we'd have a private network over here, a public network in the internet, or I guess we should go right here, and then a private network over here. And so we're connecting those and we're encrypting them through our VPN. Or if we are IT and we need remote access, say we need, well, there's a couple different ways. So remote access, we could be assisting someone. Say we work for ATK, and even though you work for ATK's IT department in Lewiston, I don't know, they have a branch, I think, in somewhere in Minnesota. And so you will actually, right, you will remote in and fix their problem, right? That's what's happening in our remote access. Or the second thing could happen is somebody is telecommuting. They're working from home, and so they establish a VPN and they remote access into the network, into the data center, and they're doing their job from home, but they're accessing the same network. Alright, so I think these are things we've talked about before. Then we have our WAN site-to-site VPN. Okay, and so it goes back to these WAN. If we go back to our first picture back here, I was talking about the WAN, and so it's connecting big sites, and it's fairly expensive. All right, so we're talking about our internet. Typically, you pay $2.50, I believe, for each meg of download, right? Whereas on our WAN sites, we're paying $250 per megabyte because it's private. So we could do frame relay. Probably not, unless you're in, I don't know, I believe the Middle East still uses frame relay, but it's basically a legacy technology. So you're using ATM, MAN, which is, as we all remember, Metropolitan Area Network, right? So that would be the MAN allows for high-speed Ethernet internet, or we could be using some sort of MPLS, basically some sort of private connection from one site to another. And in this example, apparently we have another enterprise data center in a remote location, and so we are going to use our WAN site-to-site VPN to connect that entire site. It differs from a teleworker who is just remoting in, just that computer is forming a VPN, to probably a VPN concentrator, or a what they call now an ASA, which is this adaptive security appliance. It's Cisco's main VPN solution. And so something over here in the data center would probably right in this area, we would, I guess it's in the enterprise edge, but this VPN solution is allowing this teleworker to come in, or forming a different type of VPN to connect the two networks to the enterprise data center, or probably in the same fashion this enterprise branch. So we have two VPNs. We will talk about them later, but anyway, so is there any good information? All right, let's see what they say here. Server, farm, and data center module. This area provides high-speed connectivity and protection for servers. It is critical to provide security and redundancy and fault tolerance. The network management systems monitor performance by monitoring device and network availability. The service module. This area provides access to all services such as IP telephony, wireless controller services, and unified services. Alright, so this services module, I don't know if you guys remember what some of these things are, but so our VoIP telephony, so what we could actually do, our IP telephony, I guess, voice over IP, it can sit here, and in the same manner we can go through our enterprise edge from these remote sites and have VoIP here. We could do a cheaper one where we have a router doing it over here, but anyways, we apparently are getting our information from the data center, right? That's where our VoIP servers are sitting to, I don't know, give us our voicemail, program the phone's number, and that sort of thing. Wireless controller, if you guys remember, there's autonomous access points and controller-based access points, and so a controller-based, which we always know it's controller-based. If you ever see an access point that says it is light, L-I-T-E, that means it is lightweight, and it's actually getting its image from a server. That would be our wireless controller services. And unified services usually goes into that voice over IP, but more into instant messaging, or I don't know, video messaging, those kind of things. So that's our service modules. So the enterprise edge, well, let's see how they describe what I just described. The enterprise edge consists of the internet, VPN, and WAN modules connecting the enterprise with the service provider's network. This module extends the enterprise services to remote sites and enables the enterprise to use internet and partner resources. It provides QoS policy reinforcement, service levels, and security. Okay, well, I don't know, I guess I said that. Service provider edge. Oh, I didn't talk about this. These give us our different types of networking. Okay, here's where it's going to prove me wrong from what I said before. Remember, I said plain switch network. I can see already I'm wrong. The service provider edge provides internet Public switch telephone network. Alright, public switch, not plain switched. Okay. And WAN services. All data that enters or exits the enterprise composite network model passes through an edge device. This is the point that all packets can be examined and a decision made whether the packet should be allowed on the enterprise network. Intrusion detection systems and intrusion prevention systems can also be configured at the enterprise edge to protect against malicious activity. Alright. Okay, so now what else goes into design? So basically this entire chapter is like a little tiny CCDA boot camp. Okay, so failure domains. Well, hopefully you guys, a failure domain is, as in all domains, a group of where do we have failures, okay? And so if we look at this one point of failure domain would be right here, okay? So if that internet connection went down, it would go down. Also, what would cause this network to stop working? If this router went down, we wouldn't be able to route from here to here or the internet, so we have a failure domain there. If this switch went down, all devices would go down. If either of these switches went down, we'd have a problem. And so, as you guys know, because I preach it, we need redundancy, and scaling networks is all about redundancy. Alright, and so what is this talking about? Limiting the size of failure domains. Because a failure at the core layer of a network can have potentially large impact, the network designer often concentrates on an effort to prevent failures. These efforts can greatly increase the cost of implementing the network, right? Redundancy costs money. So, I don't know, you guys can read more on that, but, well, maybe I'll read some more. In the hierarchical design model, it is easiest and usually least expensive to control the size of a failure domain in the distribution layer. In the distribution layer, network errors can be contained to a smaller area, thus affecting fewer users. When using layer 3 devices at the distribution layer, every router functions as a gateway for a limited number of access layer users. Alright, so what does that mean? Well, let's go back to our picture. Oops, went too far. Okay, so right here, these would be our distribution layer. Actually, this would be our distribution switch for each site. Okay, this is our core. This is where it's all tying in. It ties to other people. So we have distribution switches right here, right here, right here. This is the core, and hopefully there's more than one, right? Because we're just talking about redundancy. And so if that went down, be bad for this entire site, but we know that it's actually, there's probably 50 of those in there with the size of this network. But anyway, so our distribution, what it's saying is we can limit by having redundancy in the distribution. We don't have to have as big of a core, because if this distribution goes down, it only takes down this site, rather than we want some redundancy in the core, but if the core was to go down and we had a single point of failure in the core, it would take down all the sites. And so we can kind of limit stuff by doing redundancy. That's basically what that's trying to say. Alright, so what else do we have? Switch block deployment. Routers or multi-layer switches are usually deployed in pairs with access layer switches evenly divided between them. This configuration is referred to as building or departmental switch block. Each switch block acts independently of the others. As a result, the failure of a single device does not cause the network to go down. Even the failure of an entire switch block does not affect a significant number of end users. Okay, so that's similar to what I was saying. Redundancy. Alright. Well, I'm going to let you guys do this if you want to. I encourage this activity because I believe it is also on the test, right? So, well, let's see if I can get it. Alright, so We'll go campus core. Bam. Alright, number 1. So building distribution right there. Alright, so where's our access layer? Then we got our access layer. So those are the bases that I hope you guys can remember from the past. Alright, so then what is this little thing? Oh, that's a server farm and data center. That's right. So we go to Enterprise Edge. Okay, so top one, I believe that's e-commerce, right? Because we got, I don't know, I think this is supposed to be an e-commerce server and a firewall protecting it. So then we have just a straight firewall, so that's probably remote and access VPN. Nope, it's not remote access VPN, that's the internet connectivity module. Alright, so remote access and VPN would be right there. And then we have WAN site to site right here. Okay, so let's see if we got it. Bam. Thank goodness. Okay, so but if you guys really, I think there's another exercise like this, and it's not bad to know some of these things. It's up to you. Alright, so designing for scalability. Alright, so this is one of those chapters where in chapter 1 Cisco goes over everything we're going to be studying. So I believe a lot of these, like, they'll either be on the next chapter or the chapter after that. Okay, so what are we designing for scalability? Alright, over here, redundancy, so that we don't have a single point of failure. As you can see, holy cow, we got big redundancy here. What do we have? We have X's, we have straight lines across. Look at, we have, each switch has 3, or is it 4? Some of them have 4 places where they can't fail. So yeah, that's all I'm going to say about that. And then we have over here Ether channel. Ether channel is going to be very cool. It is a redundancy technology that also allows us to bundle. Okay, so what we're doing is, if we ran to, I believe you guys haven't gone over spanning tree yet, but we will study, I think it's the next chapter. And spanning tree, how a switch works is if we were to put 2 cables on, it would block one of them because it doesn't want to farm a layer 2 loop. But Ether channel allows us to bundle 2 cables so we get the speed of both the cables instead of just wasting one cable in case there is a failure. It also allows that if one of these cables goes down, we still have one active cable going immediately. And so Ether channel is just a cable bundling technique. Right here, these areas, this is multi-area OSPF. So we did OSPF last class, but it was basically based on a single area, and this is where we have multiple areas. And hopefully you remember, area 0 is the backbone area of OSPF, and so that all areas must connect to it. And so that's what we're seeing here. This right here is this is the wireless controller for these access points, or I guess that's what it's showing here. I would say that they're basing it on that you need multiple wireless controllers for your access points, or you need multiple access points on different switches, so that if this switch went down, your wireless network wouldn't crash completely. Alright, so to design for scalability, let's see. Use expandable modular equipment or cluster devices that can easily be upgraded to increase capabilities. Design for hierarchy, or design a hierarchical network to include modules that can be added, upgraded, and modified as necessary without affecting the design of the other functional areas of the network. Create an IP version 4 or IP version 6 address strategy that is hierarchical. Choose routers or multi-layer switches to limit broadcasts and filter other undesirable traffic from the network. Okay, so that's good enough. well, what do we have here? As shown in the figure, there are more advanced network designs, implementing redundant links, implementing multiple links between equipment with either link aggregation or equal cost load balancing. Okay, so that just means layer 2 or probably layer 3 is what they're talking about. Implementing wireless connectivity to allow for mobility and expansion, using a scalable routing protocol and implementing features within that routing protocol to isolate routing updates and minimize the size of the routing table. Alright, so planning for redundancy. Well, why isn't every network built exactly like this picture? Well, because redundancy costs more money. The more redundant you are, the more money it costs. But if you can, you want to do this every time. Alright. Increasing bandwidth. Alright, so now we're going to Ether channel. And like I said before, we can increase bandwidth because instead of only, say this is 100 meg or a 1 gig, it's now a 2 gig connection, and we can actually do up to 8 links in an Ether channel bundle, but I'm not going to say too much because I believe that is coming up in the next chapter. Alright. Expanding the access layer. Oh, so to expand the access layer, we throw a wireless access point on there. I'm sure you guys understand this from your own home networks. What are your typical home device? Comes with, I don't know, what, 4 switch ports, but you can add as many wireless addresses or as many wireless devices as you have addresses for them, I guess. Alright, so fine-tuning routing protocols. Okay, so what they're showing here is we have this big network all in one area, but what happens, you guys remember we're building these huge routing tables, and so we would need more expensive, each one of these devices we would need a bigger one and a bigger one the bigger our network gets, instead of doing something like this. If we do this, our routing tables are much simpler, because just like maybe you guys remember static summarization, we can summarize through OSPF, and so we can do stuff like this area will just be fed as one route to this network, or maybe we just put a default route this direction where these core routers know where everyone's at, and so when they get the traffic they send it to the right direction, and that is multi-area OSPF. Okay, so and and so in the same way as multiple area OSPF, EIGRP uses protocol dependent modules that split us up between, we have IP version 6 and IP version 4, and then the successor in EIGRP, I don't know why they're telling you this because you haven't studied it, but the successor is the route it chooses. This is the backup route, and so it keeps different routing tables, or it keeps both the tables. Either way, I don't know, what are they, is there anything else they need you to know about that? Let's see. Another popular routing protocol is EIGRP. Cisco developed it as a proprietary distance vector routing protocol with enhanced capabilities. Although configuring EIGRP is relatively simple, the underlying features and options of EIGRP are extensive and robust. For example, EIGRP uses multiple tables to manage the routing process, as shown in Figure 3. Okay, so, yep. There's an IP version 6 table and an IP version 4. And in EIGRP, they call it protocol dependent modules. But we can also have multiple IP version 4s through these PDMs, and actually we can break up the areas, but that's past the CCNA content. or did I say areas? We can break up the autonomous systems, which EIGRP runs on, as you guys will learn. Okay, so not doing this one. I'll let you do the activities on your own because I know you're reading this. Alright, so we go to switch platforms. Okay, so what are they? I'm just going to read them to you what Cisco has, right? So we have campus LAN switches. Alright, so this is what we see in class, something like this. To scale network performance in an enterprise LAN, there are core, distribution, and access, and compact switches. These switch platforms vary from fanless switches with 8 fixed ports to 13 blade switches supporting hundreds of ports. If you guys don't know what a blade is, it's one of those modules like we put in the 6509, where it gives us, I don't know, anywhere from 24 to 48 ports, or it also depends if we're doing fiber or copper, but it allows us to do all those things. That would be a switchblade. Alright, so then we have campus LAN switch platforms include the Cisco 2960, 3560, 3750, 3850, 4500, 6500, and 6800 series. Okay, and so actually now all of these are all kind of older models, and they all have an X behind them, and there's a 3560X, but also a 3650. Okay, so we have cloud managed switches. So Cisco bought a company known as Meraki, and they make switches, routers, access points, and what they do is they work a lot like a wireless controller. So what it does is they go to the cloud, and you just program them over the web. As long as they can get to the internet, you can program these and manage them from a web-based web-based portal. Okay, so they're pretty nifty. You can also do it with these campus LAN switches, but you have to buy very expensive software from Cisco to do that. Okay, so then we have data center switches. Okay, a data center switch could be built based on switches that promote infrastructure scalability, operation continuity, and transport flexibility. The data center switch platforms include the Cisco Nexus series switches and the Cisco Catalyst 6500. Okay, and so these Nexus, when you guys are doing virtualization, you can actually virtualize the Nexus switch in VMware, and but they're big, beefy switches, and typically they are going 10 gig, 40 gig, going a lot higher rates than probably our campus switches are going. Maybe our campus switches are connected through that, but they are not typically that speed. Alright, service provider switches. Okay, so service provider switches fall under two categories: aggregation switches and Ethernet access switches. Aggregation switches are carrier-grade Ethernet switches that aggregate traffic at the edge of a network. Service provider Ethernet access switches feature application intelligence, unified services, virtualization, integration, security, and simplified management. Okay, what does that mean? Okay, so these are the switches that connect the internet. If you guys are wondering what they're trying to say there, that is all they're trying to say. These use fiber, or usually fiber or Metro Ethernet, to feed to other switches, and then at some point they're going to hand off to their customers. What is this whole Ethernet, I don't know, the unified service and all that? They're saying that the service providers, if we look at them, a lot of them are cloud providers that are going to provide voice over IP or web hosting or some something to their customers. Alright, so virtual networking. Networks are becoming increasingly virtualized. Cisco Nexus virtual networking switch platforms provides secure multi-tenant services by adding virtualization intelligence technology to the data center. Okay, so virtual networking is what you guys are doing, and Microsoft virtualization, where you have a virtual switch. It's not a physical switch, you can't see it, but or it's where these switches actually, one switch does the same thing as a virtual host, right? A virtual host allows for many computers. Virtual switches allow one switch to virtualize. Routers can do it. They virtualize as if they are multiple devices. Alright, so features of switches. Alright, so fixed configuration switches. I don't think they have anything on there, but so what is fixed configuration? Just like what we have in class, right? It's not modular. We can't pull this out. It's built with 24 ports or 48 ports. So typically found on LAN switches. Alright. Here's a chassis-based switch, right? Like the 6509. And so each one of these is a blade, right? So when I say 6509, what the 09 means is that it has 9 slots to put blades in. So we could have a 6511, we could have a 6503, something like that. So each one of these is a slot that we could throw a blade in. Alright. Here is, I kind of talked about virtual stacking. This is physical stacking, and they actually have a different module now. But what this does is a stack allows, and actually it can go through Ethernet now, but it connects these switches, and so they all can be managed by one IP address. And so if one fails, you still can get in and manage it. It gives you more redundancy because they're all virtualizes one device, and so it cuts down on the amount of IP addresses you have to use to manage your switches, and it gives you a lot of options. Some businesses are actually, instead of going with 6509s or these big expensive switches, they are getting a switch with a higher switching fabric and stacking them and just using them as their core distribution. Port density, how many ports are in a switch, and as they're showing here, I don't know if this might be a 6511, I don't know what it is, but 13, I see up there 6513, so they have a lot more density than say a 24 port, alright, or 24 port switch. Okay. Forwarding rates. Alright, so how fast a switch is able to switch traffic. I think that's pretty easy. So basically data rates of the ports can be 100 meg, 1 gig, 10 gig, or 100 gig. We want to make sure the switch we buy is capable of also forwarding the traffic it is getting on there. Power over Ethernet. Okay, so I think we've talked about this before, but power over Ethernet, right, is where we just run one Ethernet cable, and we don't have to plug a phone into we don't have to use actual physical power. We don't have to go into an outlet. We power it through the switch. Same with the access point. If power over Ethernet makes access points so much easier. If you had to have an electrician come and install power where every access point was at, it would cost and just be way more of a pain than just having to run one single cable that has the ability to power a access point. One downfall of power over Ethernet, though, is you do have to look at whatever type of switch you have and make sure it actually can support a certain amount of devices, because you could actually put too many PoE devices on a switch, and if you do that, then it will start dropping a device just randomly. Some devices will start powering off, and so that's where that's one of, when you're doing PoE, make sure you calculate how much power you are actually going to use on the switch. I think the second, okay, this is something Cisco really likes, and it's called Cisco pass-through, PoE pass-through. And so on these compact switches, if we look down here, it says 2960C and 3560C. They actually don't come with a power supply. Well, you can order them with a power supply, and if you order them with a power supply, they actually don't support PoE pass-through. But some of them don't even have a power supply. And why? We can use these PoE Plus links to power them, and the reason they do this 3750X, I believe, is because it actually puts off more power than a typical switch. And so it powers, we can run 2 of these. I believe you run 2 of them, and if you run 2 cables, it will power this switch, and the switch can power, then do PoE to a phone, to a wireless access point, and still do data. And so it can actually, maybe this is just one. Let's see if it tells us. PoE pass-through. PoE pass-through allows a network administrator to power devices connected to a switch as well as the switch itself by drawing power from certain upstream switches. Alright, so it doesn't actually tell us that, but maybe it is just one. I thought you had to run 2 cables to do that, but it actually generates more power than it is taking in, right? So say in this example, it's receiving 1 PoE link and giving 2. So it's a pretty impressive thing. And so where would this be convenient? If you're just extending, like if you can't run any more cables through a wire and you have to set up a meeting or something like that, you could actually just use one existing cable to extend to some laptops in that room, or put it in a closet. Sometimes you would use this because, remember, we don't want on copper, we don't want to go over 300 feet, and so, or 300 meters, and so we can actually throw one of these in to then keep going to a wiring closet and just throw it up in the ceiling. Probably not a best practice, but gives you the options. Alright, multi-layer switching. So we've talked about multi-layer switching before, and so multi-layer switching means that, well, what is what is just switching? So switching, remember, runs at layer 2. Multi-layer switching runs at layer 2 and layer 3. It means that the switch starts acting as a router as well as a switch. Alright, so router requirements. What are they saying here? So, what is a router doing? Well, each router interface is a different network. We know that. This has to be a different network than this. And so it causes a broadcast domain, right? So it's saying broadcast containment. Where does the broadcast stop? At this switch port. Alright, so security. A switch can work, or a router can work with ACLs, or some of them have built-in IPS, or anyways, they can work as a firewall, and so they give you some security. Or you can keep people from routing from one direction to another, right? You can keep people out. So the security that a switch allows. Alright, locations. Well, what is the primary job of a router? To connect different networks. So routers come with different ports than switches, and so we can actually connect through, like this one is a serial, or basically it's saying that the router is built for WAN connections, where our switches are built for LAN connections. Alright, Logical grouping. Alright, so we can keep people in different networks. Alright, sure. Cisco routers. Okay, so we have branch routers. Branch routers optimize branch services on a single platform while they're delivering an optimal application experience across the branch and WAN infrastructure. Maximizing service availability at the branch requires networks designed for 24/7, 365 uptime. Highly available branch networks must ensure fast recovery from typical faults while minimizing or eliminating the impact on service and provide simple network configuration and management. And as you can see, these are branch routers are what we have in the classroom. Okay, network edge routers. Network edge routers enable the network edge to deliver high performance, highly secure, and reliable services that unite campus data center and branch networks. Customers expect a high quality media experience and more types of content than ever before. Customers that want interactivity, personalization, mobility, and control for all content. Customers also want to access content anytime and any place they choose over any device, whether at home, at work, or on the go. Network edge routers must deliver enhanced quality of service and non-stop video and mobile capabilities. Man, customers want a lot from these network edge routers. Alright, service provider routers. Service provider routers are ISP routers. Okay, so service provider routers differentiate the service portfolio and increase the revenue by delivering end-to-end scalable solutions and subscriber-aware services. Operators must optimize operations, reduce expenses, improve scalability and flexibility to deliver next-gen internet experiences across all devices and locations. These systems are designed to simplify and enhance the operation and deployment of service delivery networks. Alright. Small business, bigger business, internet service providers. That's basically what they're saying, right? Router hardware. Well, routers can also be categorized as fixed configuration or modular. With the fixed configuration, the desired router interfaces are built in. Modular routers come with multiple slots that allow a network administrator to change the interface on the router. As an example, a Cisco 1841 router comes with two fast Ethernet RJ45 interfaces built in and two slots that can accommodate many different network interface modules. Routers come with a variety of different interfaces such as fast Ethernet, gigabit, serial, and fiber optic. Alright, managing iOS files and licensing. This is the last chapter of this class and the least liked. Okay, basically the iOS goes through updates and you get them if you pay for your extended maintenance, and there's a lot more to it, but they have a whole chapter about it, so you guys are welcome to read that. But basically you can see you have a maintenance, what is the time frame ones? I don't remember. We'll just wait till the net. You guys can read into this or just wait till the final chapter. Alright. In-band versus out-of-band management. Alright, so hopefully you guys remember this because kind of hit it hard in CCNA3. Alright, so out-of-band means you're not in your network. You're not in your IP network, right? And so console port. Why console port? Console goes over serial. Okay, so then what else do we have On our routers, we have that emergency that can go over modems over the public switch telephone network, right? And so where does that go into? The auxiliary port. So those two ports that we have that aren't on switches, well, actually there's a console on a switch, but there's not an auxiliary port on a switch, just on a router. And it's for emergency situations. Alright, so then in band, we're in our network. We're going to an Ethernet, or I don't know. So Ethernet is based on IP, or we're in our IP. So I don't know. I guess we can go through an entire network instead of being directly connected to the Ethernet interface of the router. Oh, basic router CLI commands. Copy run, copy start. Okay. Show run, show start. Oh, look at erase startup, reload. I think you guys have all seen these many a time. Feel free to go through and set the host name, encrypt the privilege exec password, set the console password to Cisco, and set the console timeout to never. Okay, you might have to look that one up. Anyways, feel free. Okay, so our show commands. Good, we have our little thing. So show IP protocols. It's basically showing what is the router protocols. What is it running as protocols? Routing protocols. So this gives us a lot of routing information, such as OSPF 10, the router ID, routing for networks. Okay, yeah. Anyways, it gives us a whole bunch of information on the routing protocols. Alright. Show IP route. It differs because it actually shows the routes we have. Hopefully you remember that C is a connected route. L is on the newer routes, and it is a local, which is at the actual IP address that is assigned to the interface. This O right here is OSPF, and we'll go over the others when we see them in the near future. Alright, so show IP OSPF neighbors. Okay, so what is this showing? Hopefully you remember. It shows our neighbor IDs. Okay, yeah, it's showing you your OSPF neighbors. So these are directly attached neighbors and what their router IDs are and our loading state, and we can see that these are in full, right? And if they are in full, that means that routing is operational, right? The algorithm is run, Dijkstra. What interfaces we're on, and the IP addresses of our neighbors. Show interfaces. Well, I know you guys have used that many a time. So, some basic things it shows. I don't know. Whether the connect. Remember, we show up, and we show that the interface is up and the protocol is up. We show the IP address. We show maximum transition unit. We show the bandwidth, the delay, all those kinds of things. The encapsulation being ran on the interface. That we're full duplex, 100 meg, and media is an RJ45, so it's copper. Okay. And then other things, but yeah, I think you guys have seen that enough. Show IP interfaces. Oh, look it, it's the same command, but instead of showing all of them, we can actually select a actual interface. I'm sure you guys didn't know that yet, since it's CCNA3. Alright, so show IP interface brief. It'll show all of our interfaces with their IP addresses if they're up, and it just shows less than if we show the entire interfaces. It's kind of easier to look at. Show protocols. I don't know. Didn't we ever go over protocols? Oh, show IP protocols. Okay, so this is going to show if we're doing IP version 6 as well as IP version 4 and what's going on there. Alright. Show CDP neighbors. Remember, hopefully you guys remember Cisco Discovery Protocol. It's a Cisco proprietary protocol that will give us a lot of information. if we're connected to another Cisco device and CDP is enabled. What will it give us? The device name, what interface we are connected to them on, what interface we're connected to them with, and the kind of platform. And right here, if you read up here, it gives you the capability. So this one's a router. What's the S? Switch, and it supports IGMP. That must be a multi-layer switch. What is that? Cisco 1941. No, that's a router. That's Anyways, so you can try those commands out if you want to. Feel free to go over some more to the basic switching commands. I think you guys have done them quite a bit. If you're rusty, this is a great time to catch up. Some switch show commands. Let's see what we got. Show port security is going to show if we have layer 2 security enabled, right? Show port security address, more about layer 2 security. Show interfaces, fast Ethernet. What is this going to show? I don't know, errors and duplex and that kind of thing, similar to the router. And show MAC address table. This one's nice. I don't know if you guys have used this one before, but if we do this, we could actually track down. We could set a port, like if you had a user that you had to set a port to, you could just go to your DHCP table, which would give you your MAC address. You find the MAC address of that port and put that person on a certain VLAN, and it also has many other great things. I mean, if you want to track down devices, you can take your first half of your bits, right, and look down, see if this switch port is having an error. You can look, and if it says it's a HP printer NIC, then you know it's an HP printer. So it's it's a nice tool to have. How long is this chapter? Alright, so I believe this is it. Alright, so that was it. This has been quite a long lecture. Please post on the class forum or send me an email if you have any questions. Thank you.